Okay, so we have discussed the modern convolutional network architecture, including the convolution operation and its different setups. We discussed activation functions, normalization, and downsampling operations. So the next thing we're going to talk about is called skip connections, or sometimes residual connections. Um, so in the network without skip connections, I think the configuration is pretty easy to understand. We're going to look at a simple three-layer network, and the input is going to be called X, right? So in a regular network without skip connections, I think we just feed X through three layers sequentially. I think that is pretty straightforward. We could mathematically write down the equation for the first two layers as follows. So we have F1, which represent possibly the convolutional operation as well as any normalization operation such as batch norm. After that, we have the activation function, which could be sigmoid or ReLU or leaky ReLU or any number of functions we discussed. And after that, we have the functions of F2, which represent the operations that we're going to perform at layer 2, and that is followed by the same activation function as the first layer, right? So that's the operation that's happening in the first two layers. And the idea of a skip connection is that I'm going to take the input of these two layers and pass it on to the output of these two layers, and we're going to do a simple summation. Okay, so we're going to add the input to these two layers to the output of these two layers. So we would take, this is the output, and we would simply add the input to that. So that's, this very simple idea is all there is to the skip connection component. Now, a caveat is that if the input and the output are of different spatial dimensions, then we would not be able to perform the addition operation, right? Because if you wanted to add two matrices or two tensors, then they must have the same size. So a common scenario we see is that some of these layers, usually layer 1, performs a downsampling operation. It could be the pooling operation that we talked about, or it could be through increasing the stride of the layer, okay, of the convolution operation. So when that happens, the input could be of size HW, all right, and C, but the output would be a reduced spatial dimension. It could be H/2, W/2, and the same number of channels. And when that happens, we would not be able to necessarily add those things together. So we need to somehow reduce the dimension of the input as well. And a common remedy is to use another downsampling convolutional layer, which we call a de-ice layer, with some very simple operation. Okay, so we typically do a 1-by-1 convolution with stride set to 2, right? So this may lose some information, for every, because we're going to do a one, if we have like a maybe 4 by 4 feature map, we're going to do 1-by-1 convolution here, and then we're going to skip a pixel and do another 1-by-1 convolution here. So this may lose some information because it's simplicity, but we choose to kind of ignore that, okay? And after that, we could do another batch norm, but usually not an activation function, okay? So this reduces the size of the input feature map so that we can achieve the same dimension for both operands of this addition operation. So the real question is, why do we want to do skip connections, right? So basically, skip connections make it easy for the network to train. And one perspective to look at that is that this creates another path for gradient backpropagation. So imagine we have a loss function. I'm going to write this as L. And the loss function is kind of a function of the output, which I'm going to write as gx plus x. Okay. And I'm trying to, let's say I'm going to differentiate L with respect to x, which is a common operation in backpropagation, which we will talk about in our next lecture. But just to show you how gradient backpropagates or how the gradient is computed with respect to x. So this we by the chain rule of calculus, this is equal to first differentiating against f, then multiplying differentiation of f against gx plus x. We could call that z. And then we have differentiation of gx over x plus the differentiation of x with respect to x. And so this will give you the identity matrix. Okay, so if x is a scalar, it will be 1. If x is a vector, this should give you the identity matrix. So a common problem that we encounter in optimizing neural networks is known as vanishing gradient. That means the gradient gets increasingly smaller as the number of layers you add to the network increase. Okay, so this is partially because this matrix becomes really small. Okay, but since if we have this skip connection, that allows us to add this identity matrix to perhaps this matrix whose norm, some of the norms, by some definition of norm, is small. And this kind of reset the gradient in a way so it becomes large enough for optimization to function properly. Another way to think about this graphically is that, typically, without the skip connection, the gradient flows this way, but with the skip connection, we're having one more path for gradient to flow back. Okay, so this really allows us to build kind of robust gradient when sometimes the functions do not behave in a conducive manner to optimization. Okay, another way to think about residual connections that was discussed in the original ResNet paper was the following. So what they found while they try to train deeper and deeper networks is that at about 20 layers, the network stops improving. If you add more layers to the network, the performance begins to decrease. And the authors of the ResNet paper thought this was pretty weird because there is a trivial solution. When we add layers to the network, there is a trivial solution that should maintain the original performance of the network. That is, we can add identity layers that do not do anything, right? So if we add just, let's say this is a MLP layer whose connections are the identity matrix, then this layer essentially does nothing to the output of layer 3. And I can add 100 identity layers, and that should not change the performance of the network at all. However, that is not the case that we observe when we train these networks, right? So the explanation of that is somehow the network wasn't able to learn identity mappings very easily, okay? And the skip connection kind of allows that, okay? So in order to learn an identity matrix or identity operation with these network layers, if we have the skip connection, the easy thing to do is simply to set all the weights here to be 0, so that these layers are effectively non-existent, and we will have some identity mappings, right? So this way, by doing this, the authors hope to be able to train networks that beyond 20 layers. And the hope is not only to learn identity mappings, but to learn something that perhaps is a little more helpful, right? Because if you just add identity layers to the network, then obviously that wouldn't decrease performance, but that also wouldn't increase performance. And the hope is that the network learns a little more than just the pure identity mapping, and that could increase performance. And it turns out to be the case, right? So indeed, we managed to, with the skip connections, we managed to train networks up to 1,000 layers in the original papers, and there is like non-zero increase in performance. Okay, so putting things together, the batch norm, the ReLU, and the convolution weights, and the skip connections, we have a unit of convolutional architecture, which we can later replicate. Okay, so we have a 2-layer block. We have 2 ways to arrange these operations. And one thing is, the 2016 paper. The other one is also from 2016, but an slightly improved version of that. Okay, so in the original configuration, the weights basically denote the convolutional operation. It is followed by the batch norm and ReLU. So this is kind of intuitive, right? After we perform the convolution, we renormalize the output and we apply the activation function. This is kind of a canonical way of doing that. And the interesting thing, though, is that the skip connection happens right after the batch norm. And after that, everything goes through a nonlinear activation function, in this case, ReLU. The improved version, however, can be seen as putting the BN and the ReLU here, right? So the input first goes through BN, and then ReLU, and then convolution, and then repeat. And in the skip connection in this path, the input goes through no operations whatsoever. Okay, there's nothing that transforms or it transforms the input whatsoever. And this turns out to be a better way for gradient to flow back. And with this setup, the authors managed to train neural nets up to 1,000 layers. And obviously, these days, nobody uses networks of 1,000 layers, or maybe very few people do that. But this does demonstrate the power of the skip connection. Okay. So in the BN plus ReLU setup, if we omit the learnable parameters gamma and beta, or in other words, if we set the normalization to 0 mean and standard unit standard deviation, then about 50% of these the outputs of the batch norm will be negative, and the after ReLU they will become 0, right? So this may or may not be desirable. So we do have the gamma and beta learnable parameters that could control this behavior. So it may not be 50%. In some variations of the network, we could do ReLU first, followed by batch norm, and that actually does not seem to decrease performance. Some people report a small increase in performance. So we have discussed a number of building blocks for convolutional networks so far. We have the convolution layers, the MLP layers, which is known as also a linear layer, a fully connected layer, or a dense layer. So this is really just the matrix multiplication of the input vector. Okay, we talked about the pooling operation, the activation functions, the residual or the skip connection, as well as the normalization operations. So now we want to put them together to create the residual network. Okay, so this is a diagram for the 18-layer residual network. My input is an image. It could be typically for ImageNet 224 in height, 224 in width, and we have 3 color channels. Okay, so after that, we go through a number of convolutional networks, and these networks are grouped. So we have, in the first group, we have only a single layer. In the second group, we have 4 layers. Next group has 4 layers. And every group after that has 4 convolution layers. And after every convolution layer, we apply a global average pooling operation. The effect of that is no matter what is the feature map size, what is the spatial dimension here, typically it could be 7 by 7 in terms of H and W, and it could have 512 channels. Okay, so after the global average pooling operation, it takes the average of all the 7 by 7 49 pixels and take their average for every channel. So the feature map size becomes 1 by 1 by 512. And so it's basically a 512 dimensional vector. And this goes through a matrix multiplication or a fully connected layer, which produces the logits, and that goes through the softmax. Okay, so that's what's happening at the end of the network. Now, throughout the network, we have 5 major groups, or rather 4 major groups and 1 layer, which we call the stem layer. Okay. In this network, every convolution has 3 by 3 kernel filters, but the number of channels and the spatial dimensions change through the network. So typically, before every group, we apply a downsampling operation, which could be a pooling operation or a convolution with stride. So the first convolution would have stride equal to 2. Okay. And after that, we will apply padding in these convolution operations such that all the convolution in the same group operates on feature maps of the same size. Okay, but as we move to the next group, we will apply some downsampling, and we'll also increase the number of channels that's output by these convolution layers. So the rule of thumb is that we half both height and width. So the spatial resolution becomes a quarter of the previous stage, and the number of channels double. Okay, so that's the rule of thumb. So the number of channels goes from 64 to 128, and then to 256, and then to 512. Okay, so that is how the spatial resolution and the number of channels change through the network. And in this 18-layer network, we are grouping the convolution operations into 4 stages. And within each stage, we are also dividing the layers into blocks. So each of the block contains 2 convolution operations, okay? And the 2 operations are wrapped around by a skip connection. Okay, so this is what I would call a building block, and in ResNet, it's called a basic block. Okay, so this is the architecture for ResNet 18. And we have some summary in here. So in total, once again, we have 5 groups of convolution layers, and each group is operating at the same spatial resolution and the same number of channels. And the first convolution layer, which is the gray colored one, we would call that the stem layer or the stem group. There's only one layer in that group. The rest of the group starts with a downsampling operation. So the downsampling happens either from some pooling operation or a strided convolution. And at the end of all the convolution operations, we have a global average pooling. So it is called global, meaning that no matter what is the input feature size, what is the height and width, or the spatial dimensions of the feature maps, the output is always the average of all these pixels in the same channel. Okay, so it's averaging across all the pixels. So the output is always 1 times 1 times the number of input channels. And after that, we flatten this tensor to a single vector, and that gets fed into the MLP layer, which gives you the logits. And the logits goes through softmax to become a valid categorical distribution over the number of classes, over the classes. So the classes are determined by the data set. Okay. So we talked about the 18-layer network. And we also, the ResNet paper also features a number of variations that comes in increasing more layers. So we have the 34, the 50, the 101, and 152 layers, layer versions of the residual network. So we'll first look at the 18 and 34 layer variations. So the first stem convolution has a 7x7 kernel, okay? And it has stride 2, and it changes the number of channels to 64 from the input 3 channels. After that, we have a max pooling operation and has a 3x3 kernel and stride 2. So this halves the spatial resolution once again, or really half the height and the width, respectively, which result in 1/4 of the original spatial resolution. Okay. After that, there is a number of convolutional stages. Within each stage, the building block is basically the same, which has has 2 convolution layers, and this basic building block is repeated a number of times within each stage. Okay, so this is kind of their way to use basic building blocks to build large networks, is that they repeat the same block over and over. So for ResNet 18, this block is repeated 2 times in each stage, but for the 34 layer, the number of repetition is different. So it's 3 times in the first stage, 4 times in the second stage, 6 times in the third, and 3 times in the last stage. I'm not entirely sure why it has to be this way. I don't think the paper discussed this thoroughly, but this seemed to be a common setup. And after that, we have average pooling operation followed by a 1,000-dimensional FC fully connected layer. This is because these networks are designed for ResNet, which has 1,000 classes. But if your data set has a different number of classes, then this number could change, and you could be output 500 logits or 200 logits, depending on the data set that you are interested in. So the 18 and the 34 are pretty similar, and then the 50, the 101, and the 152 are similar in the sense that they use the same building block. Okay, so in the in the later three networks, the building blocks are known as bottleneck blocks. So it started with a 1-by-1 convolution that reduces the number of channel to 64. And at that 64 channel, we apply a 3-by-3 convolution operation. So the kernel filter size is 3-by-3. And after that, we restore the original channel back to 256 using another 1-by-1 convolution layer. So this is known as the bottleneck block because the number of channels that the 3-by-3 filter operate on has been reduced. So that's like a bottleneck, okay? So this is the basic building block, and this is also repeated a number of times. And it seems that the emphasis, for some reasons, happens on the third convolution stage. And that's the design of these networks.